Good morning, and thank you for joining us for the 2021 Herbert, Newby, McCoy Distinguished Lecture. As Purdue University's Executive Vice President for Research and Partnerships, I am honored to welcome you to this event, an important opportunity to learn about the exceptional work of one of your colleagues. The Herbert, Newby, McCoy Award is Purdue's most prestigious research award in natural sciences. I am pleased to have with me virtually Yong Chen, the Carl Lark Horowitz Professor of Physics and Astronomy, Professor of Electrical and Computer Engineering, and Director of the Purdue Quantum Science and Engineering Institute. Yong also serves as a member of the Governance Advisory Board for the Department of Energy QISR Center that was funded in 2020 with $115 million over 5 years. Also with me is Chris Green, the Albert Overhauser Distinguished Professor of Physics and Astronomy in the College of Science. Professor Green is the 2020 recipient of the McCoy Award. He will provide Professor Chen's introduction and moderate the Q&A following the lecture. During the event, we will accept questions through the Q&A module and address as many as possible immediately following the lecture. In addition to live streaming the event, a recording will be posted on the EVPRP website. Before I turn things over to Professor Green, I would like to offer a brief background on the award. The Herbert Newby McCoy Award was established in 1964 by Ethel Terry McCoy in honor of her husband, a distinguished Purdue University alumnus. The award recognizes outstanding accomplishments by a Purdue faculty member in the natural sciences. McCoy Award winners are nominated by their colleagues, recommended by a committee of distinguished faculty, and are approved by the Executive Vice President for Research and Partnerships and the President of the University. I will now turn things over to Professor Green.
Thank you, Teresa. It is my distinct pleasure to introduce Purdue University's 2021 Herbert Newby McCoy Award winner, Professor Yong Chen, the Carl Lark Horowitz Professor of Physics and Astronomy and Professor of Electrical and Computer Engineering, as well as Director of the Purdue Quantum Science and Engineering Institute, PQSEI. Yong received his Bachelor of Science from Xi'an Jiaotong University in 1996, followed by his Master's from MIT in 1999 and PhD from Princeton University in 2005. Yong spent 2 years as postdoctoral fellow at Rice University. In 2007, we were fortunate to hire Yong as the Miller Family Assistant Professor of Physics and Astronomy. Yong received an American Chemical Society Doctoral New Investigator Award in 2008, an NSF Career Award in 2009, and a DTRA Young Investigator Award also in 2009. He was named a University Faculty Scholar in 2013 and elected a Fellow of the American Physical Society in 2016. Yong rose through the faculty ranks and was promoted to Professor of Physics and Astronomy in the College of Science and Professor of Electrical and Computer Engineering in the College of Engineering in 2016. In 2019, he was named the Carl Lark Horowitz Professor and selected as a Willem Investigator of the Velux Foundation at Aarhus University, Denmark. He assumed the role as director of PQSEI that same year. Yong is widely recognized for his significant research achievements in both the synthesis and study of various novel quantum materials and matter. Yong was among the first to synthesize and study large-scale graphene and graphene single crystals. Yong and his collaborators motivated the use of chemical vapor deposition to grow large graphene films on metals, and they also realized the highest quality topological insulators and established iconic topological quantum transport phenomena. As testimony to his broad, truly broad interests, Yong and collaborators also performed the first systematic laser spectroscopy on lithium rubidium, which was the so-called last bialkali, and mapped out its molecular structure and energy levels. Yong and his group were also the developers of the first quantum chemistry interferometer, which is an analog of a double-slit interferometer that operates in chemical reaction space. I've had the great pleasure to collaborate with Yong myself on several projects in atomic, molecular, and optical physics, and he has truly impressed me with his careful nature, his creativity, and his tremendous drive to understand the physics all the way down to the deepest point possible in every problem. Yong is widely recognized for his contributions in the synthesis and study of novel quantum materials. His external evaluators uniformly recognize his skills with comments like, "He is regarded as one of the leaders in the development and study of large-scale synthetic graphene, and his research has played an important role in taking graphene from a research novelty to large-scale practical applications." His contributions to this field have been wide-reaching and intellectually deep. And also, Dr. Chen's remarkable and elegant experiment goes much further than any of the previous studies of quantum transport in 3D topological insulators. It's an impressive tour de force experiment that establishes a very interesting model material system for pursuing emergent physics in the future. Professor Chen is a truly unique and creative experimental physicist who has made many seminal contributions to a remarkably broad range of subjects in physics, both condensed matter, nanophysics, and also atomic and molecular physics. He's performed and led highly original and impactful studies of a wide variety of quantum materials and quantum matter. So on this note, please join me in welcoming the 2021 Herbert Newby McCoy Award winner, Professor Yong Chen.
Well, thank you very much, Chris, for your very kind introduction. And also thanks, Teresa, for the remark. It's my honor and pleasure to give this McCoy lecture. I was talking about making quantum matter. And in the start of quantum physics, I intentionally intend this matter to have a double meaning. So this means that making some quantum materials and other quantum synthetic quantum matter, but also to making them in a way to bring out the importance of quantum physics. So making quantum is really matter, as you will see in their properties. Let me first say the most important things. That is, I consider myself incredibly lucky to have worked with a team of really, really great people. Of course, the students and postdocs in my group, and also collaborators. They are too many perhaps to name on the slide. And so I acknowledge them in the individual slides when the work, specific work is being discussed. And also the support of the colleges, departments, and university, including both the Berkeley and the quantum centers in Discovery Park, and many colleagues in the research community. And of course, the sponsors for the support, and the family for the understanding and support. And also for the McCoy Award committee and reviewers. Actually, I read interesting facts about Herbert McCoy, who actually has done very nice research, mainly in chemistry, but also in material physics, kind of a nice bridge between chemistry and physics even many years ago. And that's actually kind of inspiring. I hope some content in my talk also help bridge chemistry and physics as well here. So let me start with some pretty general comments. I want to describe perhaps 3 personal stories in the general domain of quantum materials and with some connection to quantum chemistry in the end. The stories, as you may have also heard from Chris' introduction, involve making new generation of quantum materials, including graphene and exotic kind of insulator, we call it topological insulator, that help reveal some of the very interesting quantum electronic properties with the potential applications. And in the end, I want to tell the story that actually we made or find new ways to make molecules that also have a interesting connection to perhaps some new directions in quantum chemistry or even catalysis. In general, the research progress in my part research, you might call quantum condensed matter, broadly defined, are made by either developing new systems or creating some new situations. This could be new materials you make, okay, or developing some new techniques or measurement to study these systems. And they motivate or they can enable discovering new phenomena or finding new applications. And these in turn encourage we to do more to develop new systems and new techniques. The talk will probably not be necessarily a detailed technical description like in the typical seminar, but I will try to tell you these stories incorporating some of the personal kind of experience and stories, how we got into these problems and worked with really fantastic collaborators and colleagues and with students and postdoc that did something new and interesting. We think that lays also foundation for more work that I'll discuss. So let me start with a very general observation. I think it was Feynman who once said if one day he would be asked to pass only one piece of knowledge, assuming all the knowledge of human being are eliminated, but you're allowed to pass one piece of information to the future generation. And that one piece of information he suggests to pass is our world is made of atoms, which is very interesting. He didn't choose more fundamental particles, but focus on atoms. And we know, of course, both much of physics and chemistry is based on the periodic table elements. We have all these different kind of atoms making up our world. We breathe and drink molecules that are made of atoms. Of course, other life, animals, plants can do this too. So as a human being, we are distinguished in the sense we can create and utilize more complex materials made of, or create new materials made of atoms. And so the ability of making and using material is the key, you can say. In fact, we even name civilizations based on the materials that we use. This is true certainly in the old times, from Stone Age to Iron Age, so on and so forth, up to current or modern times. We have a plethora of materials now important to our societies, and perhaps we are no longer naming ourselves after just one material, but you might say if you're focused on the electronics, we're in the silicon age. But there are other materials, steel, aluminum, glass, polymer, they all play very important roles to the modern life. And looking to the future, some people may say we're entering an era that other materials are becoming increasingly important. Could be carbon, could be nanomaterials already very important, and could be quantum materials. And there's still much to be learned, and also a lot more work to actually make these materials increasingly important. And we'll focus on the quantum materials in the good part of the talk. And so you may have heard quite a bit about the word quantum and our second quantum revolution, which we're currently in the middle of the second quantum revolution. In the broad sense, any material can be a quantum material if we dig deep enough to reveal certain properties are very importantly dependent on the understanding of quantum physics. For example, electrons in semiconductors were important for the behavior that you can say this is one of actually big achievement in the first quantum revolution that happened last century. The foundation of quantum physics was laid almost 100 years ago. And one of the important technology breakthrough is the development of semiconductors that lead to transistors, for example. I should mention Purdue actually played an important role in developing some very high quality, for example, germanium crystals that were important for the first transistors. For later and today, most of our transistors made of silicon. And as time goes by, also other materials, people understand, for example, magnets, superconductors, these are also quantum materials in the sense the correlation between electrons, whether it's pairing in a superconductor or some kind of ordered spin order in the magnets, are important for their properties. Currently, we are in the second quantum revolution, where we have a much more ability to control and engineer the quantum states, quantum superpositions, even utilize the quantum correlation or even entanglement for a variety of future quantum technologies, whether it's communication or sensing or quantum computing. And in that context, there are also many, many more materials. The 2D and topological material that we'll discuss next is one example of what we call today quantum material, where they have some very new characteristic quantum correlation or even entanglement that may be important for the future quantum technology. Another way to think about many of these current quantum materials that they tend to have some exotic or emergent excitation, or we call quasi-particles. Electrons, for example, may not behave as the usual electrons in the traditional semiconductors, but may have some new kind of behavior. And that's the case, for example, for the graphene or topological insulator that we'll discuss. And there are many, many other examples of new kinds of magnets and superconductors that are also very interesting members of quantum materials featuring unusual kind of quantum correlation. Let me just highlight this point of some kind of exotic particle behavior which is important for understanding graphene and topological insulator. That in these materials, in this subset of quantum materials that I'm going to focus on next 20 or 30 minutes or so, they may be called so-called Dirac or relatives-like electronic quantum materials. In a sense, in the traditional materials, for example, semiconductor, silicon, gallium arsenide, to the group approximation, electrons have this parabolic dispersion. And you recall from simple physics, the energy of particles is proportional to the momentum square with the inverse proportion of the mass. So it has this kind of dispersion. If we recall bit quantum mechanics, particles also waves, momentum is proportional to the inverse of the wavelength of electrons. Then you can rewrite this so-called EK dispersion in this form with the Planck constant here. However, in the materials such as graphene or topological insulators, to a good approximation, the electrons do not behave like in this parabolic dispersion. So here are the conduction valence band in the traditional, for example, semiconductors. But in these new materials, they touch at one point, we call Dirac point, and near this point, the energy of electrons are proportional. It's proportional to this momentum. And that's actually a property of, for example, photons or particles that move very fast in speed of light traditionally. For example, neutrinos or some ideal version of neutrinos, that energy is proportional to momentum. And we call this ultra-relativistic region, right? Except in the materials here, the effective speed of light you put here is actually much smaller than the real speed light of the photons, the real photons in vacuum, by about 100 times. But there is an important implication when electrons are behaving kind of like photons in these materials. You might kind of guess when something moves very fast or effectively moving very fast in a relativistic fashion, the energy or temperature scale is very high. And that is in fact true. For example, the electronic kinetic energy scale for these relativistic like electrons in graphene or topological insulator can, for a typical kind of electronic wavelength, can be very high in a scale of hundreds or even 1,000 Kelvin, and at least an order of magnitude higher than the kinetic energy of electrons in semiconductors such as gallium arsenide. So that's something interesting to keep in mind, because this means you may have a chance to observe interesting quantum behavior that might be more difficult to observe now at a much higher temperature scale, potentially even room temperature. So let's start first story with graphene that people read often these days. It's a single atomic layer of graphite. In fact, even if you take a typical pencil made of graphite, if you just write on paper, you can leave trails of many tiny pieces of graphite, and occasionally they containing a single layer of the graphite, which is graphene. For a while, actually, even though graphene as a single layer of graphite it has been studied, at least it's a very well-known model for graphite and studied many, many years ago. Many actually thought experimentally it's actually impossible to create this isolated single layer graphene because a powerful theorem called Mermin-Wacker theorem says in 2 dimensions, long-range order such as crystalline order may be unstable. But nature often have a way to outsmart, kind of get around this kind of constraint. As we all know, about 17 years ago, when Guy and Lois Love, the pioneers of the graphene that revealed their amazing properties, used this very so-called low-tech Scotch tape method to exfoliate monolithic graphene from graphite and reveal many, many interesting properties of these materials, which I won't go into. I just want to point out, of course, when you use the tape to exfoliate graphene from graphite, typically they are put on some kind of insulin substrate, such as silicon oxide, silicon, and typically this exfoliate flake are quite small, some microns in size. That's certainly, even though it's enough for revealing many fundamental physical properties, but it's limiting many studies applications that may require much larger film. And also, an important question many people, including us, were asking around the early days of graphene research is that can we synthesize graphene from bottom up, particularly in a large scale? So that was actually a question was asking. About the time I actually came to Purdue, I was at Houston, finishing my postdoc at Rice at that time. I met an undergrad classmate of mine, Chen at that time at University of Houston, nearby Rice. We were having breakfast and we're chatting what I may want to do later after coming to Purdue. I said, well, there's this new material graphene came along that's pretty interesting, the single layer of carbon, but it's been difficult to growing them. People want to grow them in the large film. And Chinkai said, well, he grows carbon nanotubes on substrate using metal particle as catalyst. And that's basically a wrapped, rolled up version of graphene. Perhaps if we, instead using this metal particle as catalyst, we can spread out using a flat metal substrate. Typically nickel, for example, is the first choice we made. Perhaps we can grow graphene. Turns out people have tried this. There's a long history of this. We didn't actually even necessarily know all this history. We just went ahead and tried it, which was good. There's a lot of interesting, of course, carbon chemistry on the metal. This is actually a huge subject also in chemistry, I should mention. Late Purdue College Professor Negishi has done a lot of work on assembling much more complex carbon molecules and doing this chemistry on metals. And our chemistry is much simpler. In the simplest case, we pass hydrocarbon, for example, methane, on top of the nickel. Today we use copper, which works much better. And they catalyze some decomposition of these hydrocarbon. And you hope to have individual carbon atoms, and eventually they get assembled into a graphene sheet. The reality has been more complex, but this is essentially the idea or the hope. Of course, there are other methods to grow graphene these days, but this CVD method, so chemical vapor deposition, based on these metal catalyst of carbon decomposition is the key for this method that I'm going to discuss. So Chinkai played a very critical role, in fact, developed these techniques and also transferred them on the insulators. It worked very well. These are some examples of a very large size graphene grown on copper. Then you can further transfer by etching copper off to almost any substrate. You can call these wafer scale graphene. Of course, industry these days can even grow much, much larger size with a much bigger furnace. And today, this is perhaps the most widely used method to make large scale graphene film. You can in fact buy them from companies, so on and so forth. And you may ask, so why is this important for revealing both fundamental physics and also developing applications. So I'll give you some examples. And one of the first examples we look at is the electronic property of this kind of chemically synthetic graphene. Do they really behave just like these monolayer graphene people exfoliate from graphite? One important so-called perhaps smoking gun electronic signature of these unusual relativistic-like electrons in graphene is an unusual form of quantum Hall effect. First of all, you can make a device simply just putting a few contacts. If you have a large film like this, and also you put them in this experiment, you can transfer them into doped silicon substrate with some oxide dielectric layer, so you can apply so-called backgate voltage, tune the carrier density, tune the Fermi level across the Dirac point from valence to conduction band. So that's all fine. And what's interesting is if you, for example, pass a current through two contacts, measure the voltage of resistance across, so-called Hall effect, and you can observe these Hall effect can become quantized in these very special numbers or unit of these special numbers. In fact, unit of resistance here is Planck constant divided by a charge square. So clearly quantum mechanics play some role. There's a Planck constant here. And this constant, in fact, is actually known to many digits. Today, people want to use this as the quantum metrology kind of standard for resistance. The quantum Hall effect, in fact, have been observed in many couple of different materials in various type of 2D electron systems. But in the Dirac electron system like graphene, they have these very interesting quantum numbers, 2, 6, 10, so on and so forth. And this quantum number series is a signature of these Dirac electrons from these Dirac cone band structure, okay? It was the quantum Hall effect with this quantum series first found in exfoliate graphene, and now here is this experiment shows these synthetic graphene, even at such a large scale, have this very important characteristic relativistic-like quantum electron property just in these exfoliate graphene made from top-down approach. So this is perhaps one of the way to visualize these importance of quantum physics from the electronic properties. You can also almost more directly visualize this, pun intended. For example, in this beautiful earlier work, this is on exfoliate graphene. You can see it is almost transparent. In fact, it absorbs light about 2.3%, which is actually pretty strong for monolayer materials. But this number is also a very interesting number, is to a good approximation, pi times fine structure constant, which is another number very important from quantum electrodynamics. And there's a reason why it has this number related to these gapless band structure that I just mentioned, had this very broadband optical absorption, which the leading order approximation gives rise to this pi times alpha. This kind of property is also important for the application of graphene. People today believe it can be a very good transparent conductor or transparent electrodes, which is important for things like cell phones, solar cells, and when you need these material which is both transparent and also conduct electricity. Here's also example, quick example from my lab. You can stack multiple of these layers, then they consecutively absorb multiple units, multiples of these 2.3%. We also had a very fruitful collaboration in the last few years with Sasha Bogasova and Vlad Shalev in engineering here at Purdue, exploring the plasmonic properties of graphene based on these very large chemically synthesized graphene, which we can incorporate with the metal plasmonic structures, and their optical properties or plasmonic properties are tunable by structure shaping or electrical gate voltage. So this very strong and tunable light-matter interaction enabled by these synthetic graphene together with the metal is another very interesting application of these graphene materials. Let me quickly mention two other applications. This one is not based on necessarily the electronic behavior of these Dirac electrons, but the result from the structural property of graphene. This graphene is in fact one of the best impermeable membranes in the sense it's very difficult for molecules ion to pass through. Okay, so it's a very good seal. And the one situation where this is actually important is in the area of the bioimplants. So this is the nice work with former Purdue colleague Chen Yang, now actually moved to Boston, and they put our graphene around copper. So in this experiment is to try to suppress the ions from copper that can get into, for example, blood if the metal-based bioimplant is inserted into tissue, and that causes problem. By wrapping these metal with the graphene, it actually blocks these ions get into the blood, for example, which actually suppress toxicity of these metal-based bioimplants. That's actually important use of graphene potentially in bioengineering. A few years later, after we made these very large graphene sheets, which are polycrystalline, by the way, of course, next frontier would be how can you make very good quality, also single crystal graphene. And we tried with the Chinkai. Again, we developed these even some kind of somewhat controlled seed growth with these single crystals by growing at much lower rate or stop the growth earlier from what I showed earlier for those large size graphene film. And also we can use graphitic seed to create this array of nice, beautiful arrays of single crystals. In fact, a funny story is this was luckily made into cover with this issue of the magazine. And the editor created the title Whole Grain Graphene to describe these. And afterwards, we got some phone calls from food organizations. Kind of interesting to explain this. Whole grain means something different. So these are single crystal grains of graphene, have this very nice hexagonal shape. I should also mention by controlling growth conditions, people actually can create many different beautiful shapes of these graphene crystals. We focus on these hexagonal shaped graphenes and crystals because you can study, for example, the edge or the grain boundary, which are very interesting objects in graphene systems. Here's one example. In fact, this type of experiment, which is STM experiment, would be difficult if you put the graphene on, say, silicon oxide or insulin substrate. So our CVD graphene on metal, in this case, the growth substrate copper, provides a very good, convenient setup to do this kind of experiment. So in scanning tunneling microscopy, so this is a work that I've done by my former postdoc, Ji Tian, in collaboration with Nathan Geisinger, a scientist at Argonne National Lab, using STM they have in Argonne. So we travel there to do the experiment. And first of all, you can take these really striking atomic result images to look at the structure of this graphene edge. Okay, in this case, it's mostly along sort of the zigzag directions. But occasionally, you can find a different direction, which is called armchair. And near this edge, you observe some very interesting standing wave pattern, even at room temperature. You take Fourier transform the standing wave pattern, you get this discrete spots or wave vectors, which in fact match the distance between two Dirac cones in graphene. I did not mention earlier, it turns out in graphene band structure, there are two intercurrent Dirac cones that's separated by this momentum wave vector, which actually match the wavelength of the standing wave. So this turns out to be a direct imaging of the inter-Dirac cone electronic backscattering that we observe here, even at room temperature, okay? So that's a very good use of this type of CVD grown synthetic graphene on metal. A few years later, Jack Chung, a former grad student, working with a collaborator, Ray He, we made some bilayer, but different kind of bilayer graphene. In this case, the two graphene layers have a random rotation angle. So this is called twisted bilayer graphene. Here's some interesting band structures measured by the RPES. It's a modern version of photoelectric effect. You shine light, electron kick out. This is in collaboration with Yuling Chen's group, who did some RPES measurement on some of our twisted bilayer graphene samples. And you see when the rotation angle between these two graphene sheets becomes small, you can directly see how these two Dirac cones from two different layers get close, and the slope gets smaller with a very interesting evolution of the electronic structure. I should mention a few years later, there was striking discovery made by people, for example, Pablo's group at MIT, that showed in this twisted bilayer graphene at some magic small angles, it can become superconducting. So that's today a very, very hot field, not just twisted bilayer graphene, but many other materials. In fact, This is the one point I want to kind of highlight here, is that the graphene is just one example of now hundreds, if not thousands of two-dimensional van der Waals materials. Of course, when you reduce them, these layered material into two-dimensional form, the properties can change. And that's a big advantage of these 2D materials. You can look at them in many different kind of experimental probes. So they support, because the materials are easily accessible, everything exposed on the surface. So you can apply many different measurement techniques, scanning probe, optical, imaging, or transport, potentially even on the same device or same sample. They can be transferred on almost any substrate. So you are not limited to the traditional, for example, epitaxial lattice matched growth of these 2D systems, for example, and they're very flexible. Perhaps most importantly, and a very good new situation that I highlighted in the beginning, important for the new discovery to be made, is that you can bring different these layered 2D material together to make totally new kind of structures, materials, so-called, not just these twisted bilayers, but also these stacked van der Waals head structure, potentially in some sense going back to 3D, but not to the old material where these 2D come from, but in the new combinations, new situations. And today, this is a very active field of research. You can explore not just graphene, but magnets and 2D superconductors and many other type of 2D material. You can mix them and stack them together, create new systems. And that's one direction certainly we're also exploring. Another kind of generalization of the 2D Dirac material like graphene is to go to a 3D system where these kind of Dirac or ultra-relative electronic properties happens in all the three directions. So these are known as Dirac or Weil semimetals. And here, Dirac versus Weil just means whether you have a two degenerate or one Diracon together. And they are also predicted to have many, many interesting properties, including electronic and optical properties, and perhaps much less even explored compared to graphene. And we are currently exploring some of them. Also, some materials, their Diracon can be tilted or even become so-called type 2 with a very large anisotropy and tilted to have a different topology or Fermi surface. In the jargon of this, some of the relatively analog people call this Lorentz invariance violating materials. But anyhow, so one example of this material is recently synthesized in our laboratory, and with this type 2 Dirac fermion dispersion, and potentially with interesting electronic and optoelectronic properties that we're exploring. And this is a part of a new Muri project that's we're very excited to start recently, also with Vlad Shalev and Sasha Podaseva, looking at a variety of these Dirac Weil semi-metal material, focusing on their optical, electronic, and plasmonic properties. So with that, let me more quickly describe the second story is topological insulators that also has these, you might say, relativity like electrons, but here they live on the surface of a three-dimensional solids, and inside this solid is a gap insulator. But these materials tend to be made of heavy elements. They have strong spin-orbit coupling, and their band gap in the bulk is so-called inverted. And outside this material, for example, you have a vacuum, which have non-inverted huge gap. And at the boundary between the two, meaning the surface of the material, you have these gapless electrons running around. They are guaranteed to conduct. And this is called topological insulator. The name is a little bit contradictory, perhaps. So it's an insulator inside. It's always a conductor on the boundary or on the surface. And in fact, the dispersion of electron on surface has this graphene-like band structure. So this is bulk conduction, valence band in bulk, but in between have these surface bands, kind of look like graphene, but with a difference here. The electron spin, which is the intrinsic angular momentum of electrons, are strongly tied to the momentum. If you look at the Fermi surface at a certain, say, chemical potential Fermi level above the Dirac point, you may find these tangentially spin locked to the momentum running around like this. This is called the spin momentum locking, which is a very important property of these topological insulators. People also call this spin helical massless Dirac electrons. One analog that people studied this kind of particle before in the context of relativist quantum physics is in the case of at least simple-minded neutrinos, where you only find, for example, left-handed neutrinos. If you reverse its momentum, you also have to reverse the spin direction. And you only find the right-handed antineutrino, but not left-handed. So this is analogous to this band structure I drew for the surface state electrons of topological insulators. There, the momentum is locked with a spin. So for electrons, it's always left-handed. And when you go for electrons, instead of called antiparticle, these are holes, and they are right-handed. So this is spin moment locking. And these spin helical or spin moment locked electrons have very interesting properties and potential applications. But to get them, we need to improve the material. So one challenge in the early days of these topological insulators is that the bulk, in fact, contain many, many unintentional doping. So you can get a beautiful band structure RPS image like this, showing the entire Dirac cone and part of bulk conduction band. But when you measure its electronic property, it's very metallic. Most of the conduction coming from the metallic bulk. So people, including us, worked hard, and particularly I credit to a research staff, Irat Miotowski, worked with us for several years, growing many different kinds of bulk topological insulators. Eventually, developed these very nice 4-element based topological insulators, based on antimaterial selenide, where the bulk carrier density is many orders of magnitude lower. In fact, this is an upper bound. At low temperature is actually immeasurable. And you show a truly insulating bulk, the conduction becomes negligible at low temperature, and all the conduction from surface electrons. So that's the key. So this record lowest bulk carrier density is key to have a high quality topological insulator. Here, the band structure is dominated by, at least near the Fermi level, it's only intersecting the Dirac surface state, in fact, very close to the Dirac point. And that's the starting point for many of our device work later. And in fact, on this kind of materials, you can see when you reduce the thickness, keep cutting to different thickness, the sheet resistance can barely change because the bulk is empty. So this geometric effect was actually very difficult to observe in the earlier generation topological insulator, but now we can see this in this very good quality insulating, bulk insulating topological insulators. I won't go into much detail, but they help us to reveal these very characteristic quantum transport signatures, another version of so-called quantum Hall effect with unusual quantum numbers, so half-integer quantum Hall effect, and also a kind of an unusual version of the Aharon-Bohm effect coming from electron interference around the loop, around the surface of a topological nanowire. And these patterns are unique signature of these spin helical Dirac fermions that we can review in these high quality topological insulator these days. One of the important application of these spin helical electrons that if you pass a current, that current is automatically spin polarized. And you can measure this with a spin sensitive voltmeter. And the ferromagnet is basically spin sensitive voltmeter. And depend on the magnetization of this ferromagnet, you can measure different values of voltage or resistance, which switches when you switch the magnetization using a magnet field. But the direction switches also reverses when you change the direction of current. So this directly demonstrates spin moment unlocking. So in this sense, topological insulator is a spin sensitive resistor, you may say. But there's more. A somewhat surprising discovery is that after performing this measurement for quite a bit of time, even after removing the current, our former postdoc Ji-Fa Tian discovered that this voltage measured by this spin-sensitive voltmeter, namely ferromagnet, actually maintains a voltage that stays for a very long time, even after removing the current. And our colleague Supriyo Datta noticed this something with a voltage output, right? Even without current, it's basically battery. So we call this now a spin battery because it's measured by a spin sensitive. It only shows that you measure by a spin sensitive voltmeter, namely ferromagnet. And today we hypothesize, this is still to be checked out, but the hypothesis is that we're actually using current have a more polarized nuclear spin in the system called the dynamic nuclear polarization. And nuclear spin can live for a very long time. I should mention the late Purdue colleague, Professor Overhauser, has done a lot of foundation work on this dynamic nuclear polarization. And in our case, these nuclear polarization can have a back action on these spin helical electrons and maintain electronic voltage. And we believe the topological property, for example, the forbidden backscattering in these topological surface electrons, meaning when you local spin flip is forbidden, you have to change momentum by a large amount, helps to protect these nuclear spin polarization. So this still need more work needs to understand this, but potentially this could be used as some kind of quantum memory or spin memory, but also electronically read out or a nanoscale sensor for maybe to perform NMR compared to today's much larger size NMR machines. So this is perhaps quite long into the future, but it may have foundation for this type of applications. One more example that's very interesting these days, this is also a topic related to this quantum science center that was mentioned, is that by bringing topological insulator, particularly these spin heated electrons I mentioned, next to a superconductor, at the interface you can create an unusual kind of quasi-particle called Mariana fermions. Actually, it's an anion. And this is one of the platforms. There are other platforms you have heard that can also create these kind of Mariana anion, or even so-called there's a type of non-abelian anions. When you exchange them, they depend on history. They're no longer boson or fermions, and they're proposed to be possibly a foundation to realize a topological protected version of qubit quantum computing. So that's why a lot of people are very interested in this. And with my colleague Leon Rockinson in physics, we explored these hybrid topological insulator and superconductor structures devices and made Josephson junction and the squid, and they start to show pretty unusual transport properties that we believe is a foundation to explore some of these interesting physics next, including in this new center we have. Okay, so I'm coming to the very end of the talk. I will just very briefly to say back to the periodic table, right? One of the interesting thing mentioned at the beginning is that we can make molecules out of the atoms, and for among the very interesting kind of molecule that we physicists like, these very simple bialkali molecule you can form between two alkali atoms is a very nice model kind of molecule. And in the past few years, we learned how to make this. For example, lithium rubidium is a new kind of a bialkali molecule we made, at least in ultra cold version with Dan Elliott. And now another very simple kind of bialkali molecule is rubidium-2. But we developed a new way to make this. And this is happens in a machine we have in physics lab that creates a very cold rubidium atoms. Won't go into detail. This actually live in the Bose-Einstein condensate. But the key things of this atom system is that you can control their quantum state very well. You can see this coherent quantum oscillation between different spin or Zeeman levels of these rubidium atom can prepare in these spin states. In fact, can prepare them in a superposition of these spin states and drive the transition or create superposition using light or microwave. And one of the application or what you can do when you have this ability is this analog of the Young's double slit experiment that Chris mentioned in the introduction. Now you can put atom in this superposition, and they can go through chemical reactions. We pick the very simple kind of chemical reaction, which is spin sensitive. This is also induced by a laser light called the photoassociation. But the key point is they can react simultaneously in two possibilities, either combining two atoms with plus minus one spin or two atoms with spin 0. And these two possibilities is analog to a Young's double slit or two pathway interference in some abstract Hilbert space or chemical reaction space. When you prepare them in a superposition, in this case, we can drive them into appropriate superposition using laser light. We can react simultaneously, and there's a destructive interference between them, in this case, coming from the way angular momentum sound. And you can actually kill this chemical reaction basically completely when you drive this superposition. So we call this a quantum chemistry interferometer, which is a striking effect of the quantum superposition states, how you react these two atoms when they are in the quantum superposition state. And we hope this lays the foundation of a new approach related to a long-standing dream in quantum chemistry, is that you can control chemical reaction by using lasers. And here we don't really, like in the traditional approach, there's a big field research, use pulse laser or interferon laser field. We use one laser to drive chemical reaction, but we prepare the reactants in quantum superposition state. And there's a new program started in collaboration with Sabri Kais in chemistry, leading a program try to interface in quantum material quantum chemistry, we like to see how far we can push this idea in the chemical reaction, but perhaps even involving some materials. And this is my last slide. I say combining or interfacing quantum materials and chemistry is actually food for new direction research. You can ask a question, are there any novel chemistry catalysis that can happen in the quantum materials surface, maybe related to the unusual electronic quantum correlation? And there are many possibilities that cannot be explored. Or even using this chemical reaction as a probe to study the quantum state or characterize the quantum electricity in these materials. This is at the very beginning of the development, but there's a various idea already popping up. I think there's a large amount of uncharted territory. What happens even at low temperature, perhaps high magnetic field, some unusual chemistry that can occur. Some of them may be relevant even to astronomical settings, but some of them are important to understand the potential application of these quantum materials. People predict these topological materials can help various interesting catalysis, and this a lot of these still need to be checked out, of course, but this is a very interesting direction we're starting to explore. So with that, I will end my talk. Happy to answer any questions. Thank you.
Okay, thank you very much, Yong, for this beautiful talk about all these remarkable developments you've been a part of. We do have time for a couple of questions. If anyone in the audience has something, please enter this in the appropriate place that you can see. I have one question here to start. Is graphene superconducting? And if so, does its superconductivity have potential uses in the future?
Yes, thank you for your question. So the graphene by itself is so far difficult to be superconductor directly. However, as I mentioned, one of the most exciting development in the recent years is that if you stack two graphene layers together to form this twisted bilayer graphene, it does superconduct. And apparently it actually has a quite decent superconductor temperature normalized by Fermi temperature. So it's, in that sense, it's behaving like a high TC superconductor. So it is giving rise a lot of new insights on perhaps developing of these high temperature superconductivity. And so that is a very good recent development, very exciting topic.
Okay, thanks. We have time for a last question. Why is a topological insulator interesting, and can it have useful applications?
So yes, thank you very much. I think the most interesting thing about topological insulator is these spin helical electrons you get for free. You remove 1/2 the states available. If you give a momentum or current to electrons, they automatically select their spin states. You can get one of these allowed for each spin momentum. Why is this useful? So right there, that means if you pass a current, so in this example, if you pass current, this current is automatically spin polarized. And this is a source for spin injection in spintronics. And you don't have to necessarily use a magnet. We use a magnet to detect them, but you can use this topological insulator as an electrical controlled injector for spin. And so it has a potential application in this spin-based electronics. And other applications that I didn't quite have time to go through is that if you understand more about some of these more exotic behavior, it might be a spin or quantum memory, or it might enable electrically read out some nuclear spin, which will allow us to have reduce this very large NMR sensor to a nanoscale type of electrically detect NMR device. Or this takes probably more effort, but the pursuit in the Quantum Science Center is that this combination of topological insulator superconductor is a proposed platform to realize these more robust topological quantum qubit quantum computing. This will be another application of topological insulator, in this case by interfacing with another material superconductor.
Well, thanks very much, Yong. And now we'll go back to Teresa.
Thank you, Yong, for the broad overview, looking back in time and sharing a bit of the history of the collaborations and how you and your team have gotten to where you are, as well as a look into the future and the many programs that are supporting your work. I want to thank everybody in the audience for joining us for the Herbie Newby McCoy Award Distinguished Lecture. This does conclude our Distinguished Lecture series for 2021. So again, thank you for joining us and have a great day.